right, yesterday we laid the groundwork for talking about the behavior of gases, and we started by looking at the kinetic molecular theory, which had 4 parts. All 4 of those parts have to do with molecules that are doing what? Moving. That's why it's called the kinetic molecular theory. So molecules in motion. We said that gas molecules are really far apart, so we can ignore the space they take up. We said that their kinetic energy is related to their temperature. We said that they don't exert any forces on each other except collisions. And then after we talked about that groundwork, we talked about the 4 gas law variables, the 4 things that we can measure or change when we talk about the behavior of gases. Do you remember what they are? You could look. Volume, amount, temperature, and pressure. Those are the 4 things that we're going to be looking at for the next few weeks. Pressure, temperature, volume, and amount. And when we start looking at those 4 variables, which is today's stuff, we're just going to start by taking the variables 2 by 2. So we'll look at how 2 things are related, and we'll leave the other 2 out of it until we look at the next pair of variables. So the first things that we're doing are called minor gas laws, and they're called minor gas laws because they only relate 2 of the 4 variables. So you take 2 of the 4 things and allow those things to be changed, and the other 2 you hold constant. When you hold something constant, that means you can kind of ignore it from what you're looking at, what your story problem says. If it's staying constant, that's not changing, you don't have to consider it for that problem. The first of the minor gas laws that we'll look at is called Boyle's law, named after Mr. Boyle. This is a relationship that was first discovered during his lifetime, so that would be in the 1600s. It's been around for a while. And this is the relationship that relates pressure and volume. So those are the 2 things that we will allow to change, pressure and volume. The things that we will hold constant are temperature and amount. You did this yesterday with your mini lab. Although we didn't get to the marshmallow part, you'll get to see that part today. Yesterday with the syringe, you would pull the syringe out a little ways and then you put the cap on it. And when you put the cap on it, you've trapped a certain amount of what inside the syringe? Air. So then, if you've trapped that amount doesn't change. Did we change the temperature yesterday with the syringes? No. So those 2 things were constant. What you did change was push the plunger back in or pull the plunger back out. So which of those 2 things is that? Were you changing volume or were you changing pressure? First, you personally changed volume because you changed the size of the syringe. When you push the syringe in or when you pull the syringe out, you would change your volume. As a result, pressure inside the syringe would have changed, and that would help to create those feelings that you were trying to describe yesterday. What did you feel when you pushed it in? What did you feel when you pulled it out? So you change the volume, and the pressure changes as a result. Here's what the relationship says. If the volume of the container increases, then the pressure inside decreases. The opposite of that is also true. If the volume of the container decreases, then the pressure increases. The second part of this is probably easier to relate to yesterday. The volume of the container decreases. That would be pushing the plunger in. What did you feel as a result? Was it easy to do that? No. It got harder the further you went. The other one's a little bit harder to relate to because when you pull the plunger out, most people would at first describe that as it feels like it's getting sucked back in. You feel like there's a suction there. What's really happening is that the pressure inside goes down. And if the pressure inside is less than the pressure outside, we talked about this last year in earth science. The pressure outside would push the plunger back in, or it would feel like it's pushing it back in. Do you remember the lab we did last year in earth science where we had all those stations set up in the back? One of them was like a pop can with a hole in the bottom.
Yeah. Oh, yeah.
And then we had like a cartoon, and we had, what else was there? There was the pop bottle with the balloon inside, and you had to try to blow the balloon up. All of those kind of relied on this idea, this relationship between pressure outside, pressure inside, and the volume of that container. Okay, so let's look at why this occurs. What are those molecules doing inside that makes that relationship true? If you increase the amount of space that the molecules are in by increasing the volume, there will be less collisions between molecules. There will also be less collisions between the molecules and the walls of their container. Less collisions cause there to be less pressure. We can also describe the opposite. If space decreases, if you decrease the volume, then there will be more collisions. More collisions between molecules, more collisions between the molecules and their container. If there's more collisions, then you have more pressure. This usually works with people too. If you take a certain number of people and you squish them into a very small space, there will be more collisions. More pressure. More pressure. Get away from me. If you take a certain amount of people and you put them into a very large space, less collisions, less pressure. All right, so what are we actually going to do with this idea? We can take this relationship and use it to make an equation. So an algebra equation is what we have. And most of these minor gas laws are set up in this same manner, where you'll see some ones and some twos. Those represent like a before case and an after case. So you have, in this law, a pressure and a volume before the change, and a pressure and a volume after the change. Pressure 1 and pressure 2, volume 1 and volume 2. So we have some examples to do, 2 of them, and then we'll be done for the day. Story problems now sound like this. If a gas occupies 53.2 milliliters at 785 millimeters of mercury, what volume will it occupy at 700 millimeters of mercury? First thing you have to be able to do is recognize what pieces of information you're given. You recognize those pieces based on the units that they have. So the 53.2, it's in milliliters. Is that a pressure or a volume? Volume. The other 2 numbers are in millimeters of mercury.
Pressure.
That's a pressure. So once you've identified what pieces you have, then you have to decide which one's the before and which one's the after. It says the gas occupies 53.2 milliliters. What volume will it occupy later? So we have V1. It starts at what pressure?
785.
785, so that's P1. And it ends at what pressure?
700.
700 is P2. If you're not sure where to start with these story problems, I highly recommend making a list. Make a list of the variables that you need and the numbers that you have to work with. The story problem tells us that the volume starts at 53.2 and that we need to calculate what it is later. It tells us that the pressure starts at 785 and decreases to 700. Once you've made the list and you know what pieces you have to work with, from here on out, it's just algebra. Put your numbers in the formula where they go, solve for the one that's missing. So you plug your numbers in. I included the units with my work so you could see them. I don't grade the units until you get to the very end, until you get to your answer. What units is the answer going to be in? Milliliters, because that's the volume unit that we put into the equation. One little side note on the units here. Your units have to match for the before case and the after case. So if you're given pressure 1 in millimeters of mercury, you have to use pressure 2 in millimeters of mercury. If you're given volume 1 in milliliters, volume 2 has to be in milliliters. So your units have to match between the before case and the after case. If the story problem gives you units that don't match, you have to change them first before you put them into the equation. I didn't do that for this first one. I wanted to keep the first one simple, but some of them on your homework will have you changing units before you plug your numbers in. So watch out for that. Do we all know what to do algebra-wise from here? Kind of, sorta. I would multiply on the left first, then divide by the number on the right. Sig figs for these. We will always go back to the numbers in the question. So look at the numbers in the question. What's the least number of sig figs that we have?
3.
3, so that's what we'll keep. And you should come up with 59.7 milliliters. We have a while before we get to the test, but when we get to the test, the bare minimum of work you have to show is the step where you plug your numbers in. So when we get to the test, you have to show that step. Where are your numbers going? If you don't show the work in between, I'm okay with that. You can just show your answer, but I need to know where your numbers started out. Let's do the next example. If 2.25 liters of a gas are at 1.67 atmospheres, what will the new pressure be if the volume is decreased to 2 liters? If you're not sure where to start, make yourself a list. What things do I have? What am I looking for? 2.25 liters at 1.67 atmospheres. What will the new pressure be if volume is decreased to 2? What's P1? 1.67. What's V1? 2.25. What are we looking for? P2. And V2 is 2 liters. If you don't know where to start, make yourself a list. Write down what you have and what you're looking for. Once you get to this step, double check that your units match. Do the volume units match? Yeah. Pressure units will automatically, because that's what we're solving for. Plug your numbers in. Remember, this is the step that you have to show when we get to a test or a quiz. Solve for the missing variable. How many sig figs should we keep? 3. That's the lowest amount. As long as you do your algebra correctly, you should get 1.88 atmospheres. So we have a marshmallow lab to finish. You'll have a worksheet to do for a stamp tomorrow. Tomorrow we'll do another minor gas law, and then Thursday we'll do some labs.